This episode of Photonics Hot List is brought to you by Edmund Optics, where custom manufacturing is supported by a comprehensive range of measurement capabilities, including in-house laser damage threshold testing, custom-built industry-leading spectrophotometers, and aspheric stitching interferometry with less than 20 nanometers of uncertainty. Learn more at edmundoptics.com/manufacturing.
Hello, I'm Justine Murphy with Laser Focus World. Let's take a look at some of the amazing things happening in photonics. The complexity of machine learning and AI systems require intricate neural networks. And as these systems become increasingly prevalent, the networks must expand, which means higher energy consumption. Neuromorphic computing is an emerging energy-efficient network alternative, but it's not without flaws. Researchers from the Max Planck Institute for the Science of Light are designing a neuromorphic system that could boost neuromorphic computing, involving computers designed to mirror the structure and function of the human brain, which could potentially replace digital neural networks with physical ones. As photonics methods offer more energy-efficient and faster mathematical computation for training and evaluating a neural network, the team's new approach, detailed in the journal Nature Physics, works by changing the light transmission in the network to mark data on a light field and better process input signals. This ultimately could make the entire process for calculations and network training simpler and much more efficient. The new neuromorphic setup has already proven extremely accurate as well, in simulations requiring precise image classification. Plastics production over the past 70+ years has created more than 8 billion metric tons of unnatural polymers. Less than 10% of that has been effectively recycled, in part because plastics durability makes that process difficult. Scientists at the University of Akron in Ohio aim to change that. The team has created a system for recycling plastics and other unsaturated polymers, such as rubber, that uses a more environmentally friendly approach. It involves a photomediated oxidative degradation process under oxygen, an element that's well suited for breaking down unnatural polymers, using an earth-abundant manganese catalyst. In their work, published in Cell Reports Physical Science, the researchers found that when activated by light, the catalyst could successfully break down those polymers at room temperature. The team says their findings offer an effective recycling solution that's more practical, cost-efficient, and scalable than conventional approaches. Strong coupling between light and molecules requires tight spatial confinement of light, a high number of molecules, and the probability for those molecules to absorb and re-emit a photon trapped inside an optical cavity. With this in mind, an international group of researchers has found a way to explore and harness the unique properties of strongly coupled quantum states. Led by scientists at the University of Ottawa in Canada, the team has been able to hybridize molecules within terahertz light and in turn create a new optical cavity design. The work involved coating terahertz metasurfaces with glucose, which triggered a strong interaction between terahertz light and glucose molecules. This facilitated the design of an optical resonator, the cavity-covered metasurface, that's able to trap the terahertz light and condense many glucose molecules on the surface. The light can be trapped without precise alignment, and the researchers say the platform can accommodate other organic materials as well, to someday create a variety of different quantum systems and fundamental physics applications. And that's your Photonics Hot List. Be sure to like and share, subscribe to our YouTube channel, follow us on social media, and visit laserfocusworld.com for the latest and coolest news and information. And check out our Following the Photons podcast too, to hear some really great interviews with the industry's top players. Until next time.